Hi there. So in this section, we're going to take a deep dive into looking at exponential functions and their graphs. At the top, we look at the difference between linear versus exponential. I'll go ahead and highlight this for you. Linear functions have a constant slope or average rate of change. Slope and average rate of change are just synonyms with one another, essentially. Exponential functions, though, on the other hand, have a constant ratio of your y values. So that's what I want to illustrate down here in the example below. So in the table over on the left, you'll notice that I have given you four ordered pairs here, and I say, okay, well now let's find the slope. And so when I mean to find the slope, I'm saying, okay, find the slope of the first 2 points. And so that's what I came over here and I said, okay, the first two ordered pairs here would be 0, 0, and 1, 1. I want to find the slope between these 2 points. Well, recall your formula for slope. Remember y2 minus y1 over x2 minus x1. So you subtract your y values, so you'd have 1 minus 0 over 1 minus 0, subtracting your x values on the bottom. And that's just going to give you 1 over 1, so my slope is 1. And then move to your next data point, so 1, 1, and 2, 2. If you found the slope between those 2 points, well, sure enough, here, if I find my slope, then I'd have 2 minus 1 on top and 2 minus 1 on the bottom. So that's going to give me 1 over 1, or another slope of 1. And then look at my last set of ordered pairs, 2, 2, and 3, 3. So 3 minus 2 over 3 minus 2. And sure enough, that's also going to give me another 1 over 1, or another slope of 1. If I then go and look at the ratio of my y values, so the ratio of your y values here would be going from top to bottom. So for that first set there, that would be 0 over 1. The next set would be 1 over 2. The next set would be 2 over 3. I'm just going from y to y. So it kind of holds true then. Your linear function here has a constant slope. They all had a slope of 1 here, but my ratio of my y values were all very different, okay? Contrast that to the data over here on the right. Here's just a given data set, and I say, okay, now let's find the slope between the first two ordered pairs. And we'll find the slope between each of these sets of ordered pairs. So if I find my slope of the first order pair, up top I have 2 minus 1 over 1 minus 0. So that lands me at 1 over 1. So I've got a slope of 1 here. Then move to your next set of ordered pairs. This will put me at 4 minus 2 over 2 minus 1. So that's going to give me 2 over 1. So now I have a slope of 2. The next one will be 8 minus 4 over 3 minus 2. So that's 4 over 1, or slope of 4. And then lastly, 16 minus 8 over 4 minus 3. So 8 over 1, or just 8. So you can definitely see here my slope is not constant. It's not the same. It's changing. But look at the ratio of your y values. Okay, so from top to bottom here, the top one would be 1 over 2. The next one would be 2 over 4. But what does that reduce to? 1/2. Look at the next one. You have 4 over 8. But what does that reduce to? Another 1/2. And the last one, 8 over 16. And that also reduces to 1/2. So just trying to illustrate for you here, linear functions always have the same slope. Exponential functions will always have the same constant ratio of your y values. Just below that is some other important information about exponential functions. Exponential functions are of the form y equals a to the x. And you notice that the graph over here on the right, that your function is increasing from left to right versus the graph, I'm sorry, this is the graph on the left. The graph on the left is increasing from left to right, and the graph over on the right is decreasing from left to right. The only difference is the value of a, okay? So if you notice over here on the left, your a value is greater than 1, whereas over here on the right, your a value is between 0 and 1, so your a value is a fraction. So when your a value is a fraction, your exponential function will decrease. When your a value is a whole number greater than 1, your function will increase. You'll notice that for both of these, your domain are all real numbers. The range, likewise, is the same from 0 to infinity. You will not have an x-intercept, and you'll cross the y-axis, y-intercept at 0, 1. Another important point would always be the point 1a, that you can plug 1 in for x, and the y value would just be your a value there. A horizontal asymptote for both of these will always be the line y equals 0. So in other words, it's your x-axis. And it should be noted that both of these functions are continuous. You can graph them without ever picking up your pencil. And both of these functions are one-to-one. They would pass the vertical and horizontal line test. Okay. Just below that here in example 1, I just give you the option, but sorry, I just lost my word here, but I'm giving you the opportunity. That's what I wanted, the opportunity to graph two exponential functions, one where you see you have a whole number and one where you have that fraction, that 0.25, which we know is 1/4, so that you can see, okay, well, over here on the left, since this is a whole number, we should expect this to increase, and since this one is a decimal fraction, we should expect this one to decrease. I'll do A here with you and then let you try B. Actually, maybe I should do B since B is, it got the decimal. Sometimes that, sometimes trips people up. So I'll do B with you. So here we're looking at the function y equals 0.25 raised to the x. And we just would make ourselves a little table here, x and y. And we're just going to choose x values from -2 to +2. So -2, -1, 0, +1, +2. Okay? So what you're doing here is you're saying 0.25 raised to the -2 power. And you're just typing that directly in your calculator, and that should land you at +16. And then the next one, 0.25 raised to the -1 power. That should give you +4. 0.25 raised to the 0 power. Anything raised to the 0 power is always 1. The next one, 0.25 raised to the first power, that's just going to give you 0.25. And the last one, 0.25 squared, will put you at 0.0625. Now, if we plot these points, so I would type plot -2, +16. So that's really way off my graph up here, so I'm just going to sort of guesstimate somewhere up here. -1, 4, 0, 1, 1.25, and then your next one, 2.0625. So you get really close. So, we know that asymptote line there is the x-axis, and so sure enough, it comes through, and it's just going to hug that x-axis and get closer and closer down there to it. Okay, that would be an exponential function that is decreasing. And I'll let you go back and try letter A there. All that I have us doing down here in example 2 is just sort of a throwback. I mean, we're getting towards the end of the semester, and we don't want to forget things because your final exam will be cumulative. It's a throwback to transformations, and it says here in example 2, it says describe in words how the following graphs will be obtained from their parent function. You remember your parent function for all of these, you'll notice here, is just 2 to the x. So my parent function here is y equals 2 to the x. So we've got to think about, okay, well, what does this -3 up here in the exponent do? And that's kind of like being in parentheses there, that it would shift, so it would take y equals 2 to the x and shift, and since it's a -3, it goes opposite, it would shift it right 3 units and up 4 units. Okay? And then I'm going to let you try B and C. I think it would be a good exercise for you to go back and review that 2.5 section and take a look. And if you get stuck, you can look at the solution key there. All right, I'm going to flip it on over. Basically this page is just an application of exponential functions. So you can see here at the top your compound interest formula, and just you see it here, A equals P 1 plus R over N raised to the N times T. A stands for your final amount in your account. P is your principal, how much you initially put into the account. R is your interest rate. T is time in years, and N is the number of payments that you would get in a year. Essentially, it's the number of times that you're compounded. So over in the box on the right, these are common amount of times that you could be compounded. So if you're compounded annually, then you only get 1 payout a year. Semi-annually, 2 payouts a year. Think about it, if like a store has a semi-annual sale, they have it twice a year. Okay. If something happens quarterly, then it happens 4 times a year. Monthly, 12 times a year, and daily, 365. Okay. Moving on down then to example 3, it says suppose we want to invest $125,000 into an account at 4.5% compounded semi-annually. Part A wants us to write a formula to find the amount in the account after T years. So A equals, my P is how much I put in. He's putting in 125,000, so 125,000, parentheses, 1 plus my rate. My rate will go in as a decimal, so 0.045. I didn't explicitly say that up here, but your rate should always go in as a decimal. Go in as a decimal. So that means that you move your decimal 2 places to the left. So move it 2 places. So 0.045 divided by n. Here your compound is semi-annually, so my n is 2. So divided by 2. And then I would raise it to the n, so 2 times t. And then from here, I just would clean that up a little bit. That parenthesis can be cleaned up, so you just throw that in your calculator. So we could say that here A equals 125,000 parentheses, and if you put in 1 plus 0.045 divided by 2, you're going to land at 1.0225 raised to the 2t. Some calculators you don't have to have that 2t in parentheses, but some you do, so I think it's probably best practice for me to put it in parentheses, and then that way you'll know if you, then it will be fail-proof as far as whether you needed it or not. Part B just wants us to predict the amount in the account after 0, 5, and 10 years. So that's just a matter of us plugging in 0, 5, and 10 into our equation. So if you plug in 0, then you have 125,000. 1.0225 raised to the 2 times 0. Well, we know 2 times 0 is 0. Anything raised to the 0 power is 1. So 1 times 125,000, 125,000. At time 0, and if you think about it, at time 0, all that can be in there is the amount you put in, which was 125,000. Okay? And I encourage you, put that in your calculator. Make sure that you can get it in your calculator, because if you can't, then reach out to me so we can help you troubleshoot your calculator. Then your next one, you would just plug in a 5. So same formula, 1.0225 raised to the 2 times 5. You know what? I've got my calculator pulled up. I'll pull it up here and show it to us. So I would type in 125,000 parentheses 1.0225 close parenthesis, raise it. My calculator automatically brings me up here to an exponent. If yours doesn't, you have to have parentheses. I'm just still going to use them anyway. I technically would not need it by the way my calculator is programmed here. And then hit enter. So you would see then at the end of 5 years, you would have $156,150.43. That 8 would round you up. Okay, so if I go back to our notes, then I would say here, okay, well this would be 156,150.43. Okay, I encourage you to do for the 10 years. You're just repeating that same process. I'm just plugging in 10 for T. Lastly, here in part C, it wants to know when will the account have $200,000 in it. So we know our function. So we want to know when is it going to have 200,000 in it. So 200,000 is your final amount. That's your A value. Equals 125,000. The 1.0225 raised to the 2t. So we're trying to solve for t. And unfortunately, at this point, we don't have the mathematics yet to solve for a variable in your exponent. So you've got a couple of options. You can go through and do guess and check, which I don't think I would necessarily recommend that. Or we can use our calculator to do that. And so I'll show you a method to utilize your calculator. But just know, moving forward, that's the reason why we're going to be introducing logarithms. Logarithms allow you to solve for variables that are in the exponent. So that will be our purpose for moving forward and introducing logarithms. So I want to make this a little bit cleaner before I go straight to my calculator. So, you're trying to get closer to getting this t all by itself. So I can divide both sides by 125,000. If I divide by 125,000, it cancels out over here. I can knock out these zeros that they have in common. And then actually 200 divided by 125 is 1.6. And then that leaves me over here with 1.0225 raised to the 2t. Here's what you're going to do then. You're going to go to your calculator, and in y1, you're just going to put in 1.6. It would be the line y equals 1.6. In y2, you're going to put in the right-hand side. And then we're going to see where do these two intersect. And the point where they intersect is the value of your t. Okay? So I'm going to go to my calculator, go to y equals. So you'll notice I've already put this in here. So in y1, I put in my 1.6. In y2, I put in the right-hand side. Again, my calculator automatically creates an exponent for me, so I didn't need that 2x to be in parentheses. But if your calculator does not create the exponent, you need 2x in its own set of parentheses. Then hit graph. Pause the video if you need to, so you can catch up. Once you get here, you're starting to see, okay, I can see where my two lines here are crossing. I might want to see, we can tell it's happening over here on the right. Let me see a little bit more of what's happening over here on this right positive side. So I go to my window, and so right positive side would be your x max. I'm going to make my x max a little bit bigger, so let me go 15 and hit graph. Now we can clearly see that we are crossing right in here, and because you can see where your red and blue lines are directly on top of one another. Now I'm going to use second trace, number 5 for intersect. You can see here my function is on y1, so I hit enter. And then it's asking for the second curve. My function moved down to y2, so I can hit enter. The guess, I like to guess as close to the point that I'm trying to find as possible, so I like to come over there, and that looks about right where it's crossing. Hit enter. And then you don't take your answer until you see the word intersection at the bottom. So intersection down here, x equals 10.56. So that's telling me that when my time is at 10.56 years, I would have reached that $200,000 mark. So we'll go back to our notes here, and we solved, and we said t was approximately 10.56 years. Okay? Just below here in your notes are is me introducing the idea of the naturally occurring number e. I'm not sure if you've ever been exposed to this number before or not, but e is approximately 2.71828 and so on there. I'm actually going to use the compound interest formula to derive that constant for you, just so that you can see kind of where it comes from. And we're using the compound interest formula, so we're just saying, okay, I'm going to let my p be 1, my time be 1, my interest rate 100%, and my n is going to be my variable. So for my first, so kind of thinking about your formula here, then a equals p, so that's 1 plus your rate, so your rate will go in as a decimal, so if you move it 2 places, then you're talking about 1, over n, so r over n, raised to the n times t, and my t will just be 1. So I'm going to be, in each of these cases, I'm going to be replacing my n. And so we know annually is 1, semi-annually 2, quarterly, monthly, then I'm choosing 100 times, daily 365, hourly, how many hours are there in a year? And I'm just going to tell you this, there are 8,760. Okay. And then I'm going to utilize my formula up here. So I have, I mean, if you think about this, 1 times this is really just kind of let me just sort of clean this up over here. 1 times this piece in parentheses is just still the piece in parentheses. So 1 plus 1 over n. And then up here in the exponent, 1 times n is just n. So that's a more simpler formula that I'm going to use down here. So I have then, for the first case, 1 plus 1 over 1 raised to the first power, or 2 to the first power, which will just be 2. Okay, let's go semi-annually. So 1 plus 1 over 2 raised to the 2. You would put that in your calculator. You should land at 2.25. The next one, 1 plus 1 over 4 raised to the 4th. That should put you at 2.4414. And let's do monthly. So 1 plus 1 over 12 raised to the 12th. That'll put you at 2.6130. It's probably worth for you maybe pausing the video and putting these in your calculator, making sure that you can get these numbers. Then your next one, 1 plus 1 over 100 raised to the 100th power. That should land you at 2.7048. And then your next one, 1 plus 1 over 365. You'll notice here my n just keeps getting bigger. And then I have 2.7146. And then lastly, let's make that n really large. 1 plus 1 over 8760 raised to the 8760. And that should put you at 2.7181. And that should start to look very similar to this e value up here. And just below that, that E is a natural base that we're going to be utilizing with natural logs in the coming sections. It's very similar to a naturally occurring number like pi, or a transcendental number like pi. Is used in a lot of applications like population growth, radioactive decay, compound interest. Our definition of E is the limit as n goes to infinity. Notice how my n value kept getting bigger and bigger and bigger as my limit as n goes to infinity of 1 plus 1 over n raised to the nth power is approximately, get back to my pen, approximately that 2.718281828. Okay, that's our approximation there for E. Okay. In example 4, I'm just having you practice with your calculator to make sure that you know how to put these values in your calculator. I will make sure that everybody knows where their where E is in the calculator. So let me pull up my calculator and get out of there. And to find your E, you're going to hit second ln. That's the ln is your natural log. It's 2 above on. Okay, and then I'm going to type in my negative 2.5 and hit enter. And I've got you rounded to 3 decimal places, so we'd say here 0.082. That would be our answer there, 0.082. Okay. And then lastly here in example 5, you are utilizing the formula here. Your time is measured in months. So in part A, if they want us to find the value of the stock in 2 years, you'll need to convert those years into months because that your time in the formula is represented in months. So convert that there. Letter B, you're going to be forced to utilize the technique that I showed you a minute ago of putting the left-hand side in Y1 and the right-hand side in Y2 so that you can figure out where they cross. Okay. And you might have to adjust your window a little bit to be able to see it, but I think that'll be a good practice for you there. All right, let me know if you need anything. Thanks a lot. Bye.